Okay, this is outline of this talk. I will first introduce what is dense prediction task, and then present the dilemma of convolutional neural networks in dense prediction. Also, I will present our recent work in CVPR 21 and ICML 21 just observed a few days ago for sparse predictors for dense prediction. Basically, we perform dense prediction without using convolutions. Okay, here we show the popular keywords in CVPR. CVPR is a top conference in computer vision from 2018 to 2022. And we would like to point out that actually almost all the papers presented in CVPR use convolutional neural network to extract features from image or video. And we will also need to highlight 3 basic fundamental tasks in computer vision. For example, image segmentation, image classification, and object detection. Okay, and I guess many researchers in computer vision believe these are 3 most fundamental tasks in computer vision, and the recent advanced topics such as 3D computer vision and video understanding are most of them based on these 3 basic fundamental tasks. Okay, here is the definition of dense prediction, which involves all the basic fundamental tasks of computer vision. For example, image classification, which is to assign multiple category labels to a single image, say in this example, person, sheep, and dog. And also this is about object detection, which is to predict a set of object bounding box and the category label for each bounding box. And here we have image segmentation, which is to assign each pixel a class label. And instance segmentation, which is to predict a set of object bounding box and their corresponding class labels, and also the foreground and background pixels within each bounding box, so that you can imagine that instance segmentation is the combination of object detection and image segmentation. Okay, here we present the challenge of dense prediction by using a very simple example. Okay. Here we want to detect and segment triangles in an image. Although this is a simple example, it is already sufficient to highlight the challenges in dense prediction. And the first one is that different object instance of the same object category. Here in this example, we need to detect only a single category, that is triangle. Different triangles in this example have different appearance. For example, different colors, different shapes, aspect ratios, and size, which means that dense predictions has large interclass variations. So many popular approach in dense prediction, need to partition the image into grid with different number of cells. For example, in this 2 by 2 equals 4 cells. And they apply the convolutional network to each cell to extract feature vectors of that cell. And the convolutional network is trained to predict the object category, say triangle in this case, and also the tight bounding box of this triangle within each cell, and also the foreground and background pixels in this tight bounding box. However, as we see in this simple example, we have many different triangles with different aspect ratios and different size. That means we may need to partition this image into different grids with different number of cells. So for example, we may need to partition this image into 4 by 4, 8 by 8, and 4 by 2 cells in order to cover all the objects instance with different aspect ratios and different size. Even for a simple small image, say only 1000 by 1000 pixels, we may have millions of potential object bounding boxes in this image. However, for a single image, we only have a few ground truth bounding boxes, which means that we only have a few positive samples, positive bounding box in training, such that this problem is an extremely unbalanced machine learning problem. And the second challenge is that different objects may present at the same pixel location in the image. That means dense prediction has large occlusions. For example, the CNN to extract features from each cell actually looking at this clustered foreground and background. And we may know that the popular dense prediction methods have wide applications. such as in the autonomous driving, video understanding. And most of them have large impacts. For example, these are the popular dense prediction methods presented a few years ago, such as R-CNN, fast, R-CNN, faster, R-CNN YOLO, SSD, and mask R-CNN. All of them already have citation in Google Scholar more than 10,000, okay? And actually, for researchers, it's not easy to achieve, 20,000 citations, even in the entire research career. And for these guys, only a single publication already achieved more than 10,000 citations. And here we compare the limitations of previous popular dense prediction methods as we mentioned before. Okay, we compare the detailed diagram of the systems, and we show that existing dense predictors have many handcraft, or we call black box components. The first one is that, as we highlight in the green region, all of them use convolutional network to extract features from image. Okay. Before we talk about the problems of convolutional network in dense prediction, we have to recap the definition of convolutions. For example, we have an image with height and width denoted as h and w. The first step is we need to perform padding 0 at the boundary of this image. If we perform a 3x3 convolution on this image with stride 2, we just put these 3x3 convolutional kernels at every 2 pixels in this original image, and the output is 4x4 pixels. If the convolutional function is followed by a pooling function, then the size of the image will be further reduced to 2x2 after pooling operations. You will see that convolutional operation always reduce the size of the image, that is the image resolution, in this example from 7x7 to only 2x2. And we actually have many different convolutional functions. And in this talk, we want to highlight that many different convolutional functions have an unified formulation. For example, if we extend the image dimension to D in channels and the output of the image to D output channels, and then we can denote the image as X, okay, which is a 3-dimensional tensor. And also W is the convolutional kernel, which is the 4-dimensional tensors. Okay, K here is the kernel size and D in channel by D out channels. Okay. And here is the definition, the formulation of convolution. We need to extract the feature vectors at each pixel location of the image. And the feature vector of a pixel at the location by using convolution is just the vector matrix product. Quite simple. The vector matrix product between the image X and the convolutional kernel weight matrix W. And different convolution, the definition of different convolutions actually is the definition of the delta K. This is a set representative of set of parameters in the small kernel W. You will see that, for example, if we have a 3x3 compact kernel, okay, only we have 3x3 equals 9 parameters in the small kernel W, and we can represent different convolutional functions by using different offset delta K, okay, to represent different these convolutional functions. If we put this 3x3 compact kernel at every location of an image in a 3x3 region, this is called the receptive field RF, okay, and we can define the delta K offset like this, -1, 0, and 1, okay, which is called the regular convolution. If we need the same 3x3 compact kernel to look at 5x5 receptive field of the image, then we can define the delta K like this, okay, -2, 0, 2. This is actually called the dilated convolution with stride equals 2. And if we need to increase the receptive field to let this 3x3 compact kernel to look at 9x9 regions in an image, we can define the delta K offset like this, -4, 0, 4, such that this is called the dilated convolution with strides equals 4. And if we define any numbers, any fractional numbers in values in this delta K, which means that we want to put the value of the original 3x3 compact kernel to any location of the image, such that we have the deformable convolution, okay? So that here we just show you that actually we have a unified formulation for different convolutional functions, and we just need to change delta K. Even delta K can be arbitrary values, fractional values, to represent deformable convolution. And here we summarize the problems of convolutional neural networks. Okay, the first one is that CNN always reduce image resolution, as we showed before, so that losing important information. And CNN need to stack many convolutional layers in order to increase the receptive field, as we show you in the previous slide. And however, sequentially stacking layers make computation inefficient in hardware. And also we need to manually decide different convolutional functions in CNN for different tasks in computer vision. For example, we need to use design, say, dilated convolution, deformable convolution, and 3D convolution for different tasks, for example, video understanding. And also the computations of many convolutional functions are not easy to implement and optimize in hardware. Okay, let's go beyond the convolution. Okay, here we introduce the replacement of convolution by using the self-attention operation. We need to recap the equation of convolution first. If we use convolutional function to extract feature vector of a pixel, which is just equivalent to the vector matrix product between the image and the parameter weight matrix, right? And here, if we use the self-attention operation to extract feature vector also offers single pixels in the image, okay, which is equivalent to the scalar vector matrix product, okay, between the image and the kernel weight matrix. And the difference that in the self-attention operation, we need to average all the feature vectors of the pixels in the entire image of the with respect to the certain pixel Q here, instead of only looking at a small kernel W, say 3x3 compact kernel in the original image, such that if we compare the illustration of convolution and self-attention, if we need to calculate the feature vector of the pixel XQ here, in convolution, it only looks at 3x3 region, small region in the original image to calculate the output of this feature vector of XQ. If we use self-attention to extract features, okay, of the same location in the image XQ here, actually XQ look at the entire image region H by W, okay, to calculate the feature vector. And this is done by a so-called attention map A here. A is just the matrix multiplication between the original image X, okay? So here is the detail of the computational roadmaps of self-attention. We may skip the details. And here we would like to highlight that self-attention actually can learn to represent any kind of convolutional functions with the attention map A, and A is just computed by using matrix multiplication, so that which it can be easily accelerated in hardware. Okay, we have mentioned that the first limitation for the previous dense predictors is that all of them use convolutional networks to extract feature from image, as we highlight in the green region here. And the second limitation is that all of them use the dense proposal stack, as we highlighted in the yellow region. Okay, as we mentioned that we may have millions of potential bounding balls that cover the object, and the step of dense proposal is to select those bounding balls with large probability to cover the objects in order to reduce the computational complexity. Okay, and we would also like to point out that the limitation is that all of the popular approach of object detection and segmentation use one-to-many bounding balls assignment. This, as we highlighted in red region, this means that, as we mentioned, that a single image only contains a few ground truth bounding balls, making the problem of dense prediction actually is an extremely unbalanced machine learning problem. However, to increase the number of positive samples, popular approach would assign one ground truth bounding box to many potential bounding boxes in order to increase the number of positive samples to reduce the problem of unbalanced machine learning. So that, however, this stage turns out that it will increase the false alarms in the testing stage. And therefore, all the approach need to use the maximum suppression, okay, MMS, to reduce the false alarm in the testing stage. And here we point out that the first limitation is based on deep learning models, and the second and third and fourth limitations are based on manually decided components, okay, which are not deep learning models. And here is the model comparisons. For the existing work for dense prediction, typically before June 2020, okay, most of them follow this pipeline. They use convolutional network CNN to extract feature from image, and followed by many manually decided components. For example, dense proposal and one-to-many bounding box assignment in order to increase the number of positive samples. And then the maximum suppression, because one-to-many bounding box assignment increase the false alarm. So then the maximum suppression need to use to reduce the false alarms, okay? This is the pipeline of most of the popular approach before 2020. However, the problem is that our recent work, what makes for end-to-end object detection, are presented in ICML 2021, okay, this year, point out that many of these manually decided components actually contribute large portion of the accuracy of the existing detection systems. For example, MMS contributes 30% to 50% precision to the dense prediction systems, which means that high performance of the existing dense predictors does not from deep learning models, okay, but from the handcraft manually designed pre-processing or post-processing steps such as MMS. This just violates our knowledge that the recent breakthrough in the last 10 years in dense prediction actually comes from the advancement of deep neural networks. As we can see here, we compare the performance of recent popular approach called CenterNet and Focus with and without the maximum suppressions. And we see that if we remove the component of the maximum suppression, the performance dropped a lot. Okay, this is the new pipeline after June 2020 based on transformer model. Transformer model is a model that consists of many self-attention operations, as we mentioned, okay? And this work just showed that we can combine both convolutional network to extract feature from image and then the transformer model to make prediction of the bounding box. And we can just, if we do this, we can just remove all the manually decided components, including the dense proposal, one-to-many bounding box assignment, and the maximum suppression, okay? And also achieve similar performance compared to, even better performance compared to the recent popular approach, which means that this performance, all of this good performance original from the deep neural network, but not these manually decided components, okay? So this is called end-to-end dense prediction. End-to-end dense prediction means that we just perform deep neural network model to extract feature from image and then output the location of the bounding box without any manually decided components as the pre-processing or post-processing steps. And our recent work called Sparse R-CNN, okay, in 2021, proposed that we can actually use either the CNN or transformer, but not combine both CNN and transformer to achieve this end-to-end dense prediction, as well as we remove all these manually decided component, okay, including dense proposal, one-to-many bounding box assignment, and the maximum suppression. And here is, this is the most fast and accurate detection pipeline so far. And we see that when we compare the performance, okay, see Sparse R-CNN with and without the maximum suppression, the performance comparable, almost the same. And the performance outperform those based on transformer model, deformable DETR. And we also prove theoretically that in our ICML 2021 papers, the key for end-to-end dense prediction is the dynamic one-to-one mapping. This is kind of counterintuitive because the original one-to-many bounding box assignment is to increase the number of prosthetic samples in training in order to reduce this unbalanced training problem. However, we find that one-to-one, that is one ground truth bounding box only assigned to one potential bounding box in training. Actually, this is a dynamic mapping. That is, in each iteration during the training, we will refine this one-to-one mapping, okay? And we prove that this is actually the key to achieve this end-to-end dense prediction in order to remove all the manually decided components to improve the dense prediction systems. Here is the simple diagram for the backbone network of Sparse R-CNN, okay, which we divide the image into grid, and then we use multiple self-attention operations to extract feature vector from each cell. We may skip the details. And here the comparisons for object detection in MS COCO dataset. Okay, the first figure here shows that the Sparse R-CNN is compared to many popular approach, including RetinaNet, fast R-CNN, DATR, and deformable DATR, and we highlight the best performance for different evaluation matrix. And the second figure shows that we compare the performance of DTR based on transformer and Sparse R-CNN. This is based on convolutional network without transformer, okay? And we compare the performance with and without positional encoding. As we mentioned, DTR is based on transformer, and although DTR remove all the manually decided components, however, positional encoding is a new manually decided component introduced in transformer, which means that DTR remove the existing manually decided components, but introduce a new one. Okay, however, we see that if we remove positional encoding in the transformer model, that is DTR, the performance drops a lot. If we remove the positional encoding in Sparse R-CNN, we see that the performance can be even improved. And the third figure is that we show that the key for achieving end-to-end object detection is not convolutional neural network and not transformer. In Sparse R-CNN, we can use either one of them, okay? However, if we use transformer models in Sparse R-CNN, we can improve the performance. For example, if we use swing transformer, we can improve the performance compared to the CNN model when we use CNN in Sparse R-CNN. Okay, we end this talk by presenting some take-home messages. The first one is that previous test predictors are not end-to-end. Okay, typically the method before 2020, because there were many indispensable manually decided components which contribute up to 50% of the system's performance. And CNN are not necessary for dense prediction tasks. These two actually violates our knowledge that CNNs are indispensable in the recent breakthrough in computer vision, okay? And the third message is that although transformer or the self-attention operations starts dominating computer vision tasks after 2021, it is still not a universal architecture to general AI. We may need to go back to where we came, that is multi-layer perception, which is a more general architecture than self-attention and has more representative power than self-attention. The answer, we believe the answers to general AI is how to impose regularization to increase the generalization capacity of multi-layer perceptrons. Okay, thank you. This is the end of my talk.